Okay, before we get started today, I want to address a point I've been seeing on some of the homework. Some of you, when you're doing your Lewis structures, you've been putting in your bonds and all that, but you haven't been putting in lone pairs. Don't forget about lone pairs. You need those in there because, first of all, you got to use up all your electrons, but second of all, you got to make sure everyone has an octet, 8 electrons around them, and without lone pairs, you won't be able to do that. So after we get through this final lesson here, I want to, and it'll probably be after spring break. I'd like to get together do a Zoom meeting and really discuss some of this stuff because I think some of you are a little shaky on it. Now, yesterday we looked at resonance, when you can write 2 or more structures for the same compound or the same substance and they both are valid. Sometimes their structures are equivalent and it doesn't really matter which one is, they're both equally valid, but sometimes one is more valid than the others. And so how we can decide that is by looking at something we call formal charges. Now, this isn't from the PowerPoint of your textbook. This is from my older PowerPoint that I used to teach this stuff from. But I want to cover this topic in here so you're aware of it, even though your book doesn't. Formal charges are fictional charges that we put on an element in a compound. They're not real charges. They don't exist. They're not there at all. We put them there only so we can keep track of who is electron deficient, who has too many electrons, or whatever. So again, they're bookkeeping. They're keeping track of electrons more than anything else. It's called formal charges. Now, what it is, it's the difference between how many electrons are around the atom in the compound versus how many the atom came in with. For example, oxygen comes in with 6 valence electrons, right? S2P4. In a compound, if it has 6 also around it, it's good. If it has 7, it's got 1 electron too many, so it would have a formal charge of -1. Now, how do we figure out how many electrons are around the atom? Well, we assign them in this way. The lone pairs, non-bonding pairs, those electrons all account for that atom. Shared pairs or bonding pairs, you essentially pretend that you break the bond and give each atom custody of one of the 2 electrons. You're not really breaking any bonds, you just, you pretend you're doing that, and then each atom gets 1 of the electrons. Okay, and then you can assign electrons that way and then decide how many it has compared to how many it used to have and assign your formal charge. I'll do an example in just a moment, but notice this last point on this slide anyway. The total formal charge of the compound has to add up to the total charge on the compound. So if it's a neutral molecule, whatever number of formal charges you have, they better cancel out to 0. If you're doing it with a carbonate ion who has a -2 charge, your formal charges need to add up to -2. Okay, so let me show you a real quick, easy example, and then we'll go into some more complex ones. Let's look at the sulfur dioxide molecule. We did this one already, right? So you have sulfur in the middle, oxygen, oxygen. Now, we already established we have 6 times 3 is 18 electrons on this. We talked about that when we first did it a couple days ago. So, what did I say? 18 electrons. I better write that down. So, let's make our bonds. 2, 4. Now, lone pairs. 6, 8, 10. Notice I put my lone pairs on there. That gave this guy 2, 4, 6, 8 electrons around itself. It has a full octet. Without those lone pairs, it's not a valid structure. So, how many electrons did I use so far? 2, 4, 6, 8, 10. 12, 14, 16. That oxygen has an octet around it, 2, 4, 6, 8. I've used 16 electrons. I got 2 more, so 18. Notice sulfur has 2, 4, 6 electrons, not 8 electrons. So what do? Well, let's get rid of, say, this lone pair right here. Again, on a whiteboard it's easier to do, and make a double bond. Now, that's okay for oxygen because it has 2, 4, 6, 8. It's still got its octet. Sulfur now has 2, 4, 6, 8. It has its octet. And I didn't mess with that oxygen, so obviously it has its octet also. So making that double bond, this is a review of stuff we already did. You get your full octet on everyone. Now, notice there's resonance here, although it doesn't matter a whole lot because it's symmetric. Drawing all my lone pairs. Notice again, since I already know how many lone pairs and bonding pairs I have, I can just rearrange them, slip them around from one oxygen to the other. And there exists resonance between these two structures. Now, let's try to assign formal charges here. We'll start with sulfur. Now, remember, each sulfur and oxygen are in the same column. They both come in with S2P4, which is 6 electrons. So sulfur came in with 6 electrons. How many does it have now? Well, it counts these two as its own, so that's 2. The bonds, we cut the bonds in half, at least in our minds, and each electron, one goes to one atom, one goes to the other. So this bond contributes 1 electron to sulfur, this bond contributes 1 to sulfur, this contributes 1 to sulfur. So I have 1, 2, 3, 4, 5 electrons on sulfur. Remember, it came in with 6, it only has 5 now, it's short 1 electron. So it has a positive formal charge. We usually put them in circles. Okay? So that sulfur has a positive formal charge. What about this oxygen? Remember, it also came with 6. It has these two, that's 4, split the bonds, 5, 6. So it has 6 electrons, it came in with 6, it's happy. And so no formal charge on that oxygen. This oxygen over here also came with 6, it has 2, 4, 6, plus 1 for the bond, that's 7. It has more electrons than it started with, 1 more electron than it started with, and so it has a 1 negative formal charge. And that's how you do formal charges. Notice the sum of the formal charges plus 1 plus negative 1 equals 0. 0 is the charge of the total molecule, so it works. The other resonance structure, well, the exact same discussion is going to apply, isn't it? I mean, verify for yourself that this is true, but that sulfur has a plus, this oxygen has a negative, and the other oxygen has no formal charge. So, which structure is better? Neither is better because they both have the same number of formal charges and the whole works. So, that tells us that these structures are exactly equivalent and they both contribute equally to the structure of the real world molecule. If one of these had been better than the other, then it would contribute more. Now, let's look at a maybe more complex example. Let's look at carbon dioxide. Again, we did this one before. Now, to save some time here, I'm going to just give you what we already came up with. We had 2 double bonds, lone pair, lone pair, lone pair, lone pair, right? And then we decided it was also possible to do a triple and a single, 1 lone pair, 3 lone pairs. And then I'll put it down here because I ran out of room. It was also possible to do a single and a triple, 1 lone pair, 3 lone pairs. Again, if you need to see how we got that, look back at yesterday's lesson. We did this molecule. And again, we could put the double-headed arrow between all of them and call it resonance. Let's look at formal charges. Carbon comes in with 4 electrons, S2P2. It has 1, 2, 3, 4, breaking those bonds up, so it's good. Oxygen over here came in with 6, 2, 4, 5, 6, it's good. Oxygen over here, 2, 4, 5, 6, it's good as well. This molecule needs no formal charges. Sometimes that happens, and life is good when that happens. What about this one? Well, carbon, 1, 2, 3, 4, it's good. This oxygen, 1, 2 for those 2, plus 1 for each bond, 3, 4, 5. It came in with 6 electrons, it only has 5. It must have a positive formal charge. This oxygen, 2, 4, 6, 7. It came in with 6, it now has 7, it must have a negative formal charge. So this form of the CO2 molecule has formal charges, 1 plus and 1 minus. The other one down here, well, the same discussion is going to apply. This one over there, here is negative, that one over there is positive. So you'll notice these two structures are equivalent. They'll contribute equally to the molecule. But this one has fewer formal charges. In this case, none of them at all. Turns out that having fewer formal charges is better. You get a more even distribution of electrons within the molecule, and that's more stable. So all things considered, this resonance structure is better than the other two resonance structures. Now, does that mean the molecule's only this and the others don't exist? Not at all. All three of these are valid. All three exist. And we said yesterday they average together to give you the true molecule. Well, what I kind of didn't tell you yesterday is they don't average equally in there. When we average them together, this molecule, this structure will contribute more to the real molecule than those structures will contribute. How much more? I don't know, but certainly more. The better the structure, the more it's going to contribute. The worse the structure, the less it's going to contribute. What would make a structure worse? Well, we'll look at the list in a moment, but certainly having more formal charges. If I had another formal charge over here, that would make it even worse yet, and it would contribute less to the overall structure. So let's look at that list on the next slide and see what is the most plausible structure, which means which structure is the best one of the ones available to us. The most plausible structure would have the fewest formal charges. With carbon dioxide, one had no formal charges, the other had two, one of each. The one with fewest is the better structure. Having formal charges of smallest magnitude. Sometimes you get formal charges of +2 or -2 or even worse. If you have a choice, one structure has a -2 charge and another structure only has a -1 charge, that's the better structure. The one with the smallest magnitude charges. Okay? Also notice fewest charges. So if you have 3 different charges versus 2 different charges, that's better. But also smaller magnitude of charges, 1 minus instead of a 2 minus. Now, negative formal charges are always best if they're on the most electronegative elements. Okay, so that makes it a more plausible structure. If you got to have a negative charge, it should at least be on the element that has the greatest electronegativity. If there's a fluorine in your compound and it's not the guy who gets the negative, well, that's not good, because fluorine has the best electronegativity of them all, right? Heaven forbid you put a positive on a fluorine. The best structures, the most plausible structures, will have a negative formal charge on the more electronegative element. And then the last rule, well, not really rule, but guideline to go by is you should avoid having adjacent charges of the same type. If you have 2 positive charges side by side, that's not good. The 2 atoms are going to repel each other. So, again, draw your Lewis structures. Make your resonance structures if it's going to be. And then assign formal charges. And then use this list of rules to see out of those structures which one or ones is the best structure and which are the worst structures. And then you can use that as guidance from there to determine what the actual bonding in the molecule is going to be like. Notice again, you go back to your carbon dioxide, we decided it's going to be more like a pair of double bonds. And yes, there's going to be some characteristics of triple and single bonds in there, but for the most part, it's going to behave very much like it was a pair of double bonds. Okay? For tonight, I'm going to give you a few problems on a little worksheet, maybe 5 or so, where I want you to do this. I'll give you a few compounds, and they're all going to have resonance, and your job is to draw all the possible resonance structures, whether it's 2, 3, 4, whatever. And then assign formal charges and tell me which is the most plausible and which is the least plausible structure. Okay, and again, that just indicates which structure contributes more to the overall molecule than the others. All right, that'll do it for today, and I'll talk to you tomorrow.